That's not bad. So okay, welcome everyone. So to the operating system class. That's again exciting class. Cannot say that it's very easy, but you guys enjoy it. So let's do a little bit of an introduction. So I'm an assistant professor. I just recently joined School of Computing last fall. Before that, I was an assistant professor at the University of California, Irvine. But I actually graduated from the University of Utah, so I was a PhD student here for quite a bit, from 2005 to 2013. It took me a while. I enjoyed it a lot. I like skiing. I like all the outdoorsy activities which Utah offers. And after moving around, I just decided, okay, it's worth coming back to Utah. I want to live here. So, and that's why like my family and I, we came back. So, and what I do for a living, essentially, I mean, I'm a professor, obviously, right? But the thing is that since early on in my life, I decided I want to build operating systems. I mean, it's hard to explain why. Maybe back in the days, operating systems were as exciting as machine learning today. So it was the thing to build. And so when I was a student and I was actually in a applied mathematics program, I decided, yeah, I'm gonna be doing operating systems, and I built them ever since, roughly from 2000, right? And I built a bunch. So I was working on the bits of L4 microkernel, and L4 is the first formally verified microkernel. I didn't get lucky to work on the verification part, but I was lucky to work with a team, build micro ITRON specification for them. I was working on Zen virtual machine monitor, and as my PhD, build a deterministic replay engine for Zen. Zen is one of the mainstream virtualization solutions. It's essentially KVM and Zen, and Zen was deployed and still is probably deployed by Amazon Cloud. And replay means you can record the execution of a virtual machine, and then later on replay it exactly as it was in the first time during the original run. I built, then with my research team, built a bunch of extensions to the Linux kernel main, aimed at essentially isolating device drivers, essentially taking part of the Linux kernel, running it in isolation as a mechanism to prevent certain classes of attacks on the kernel. The most recent one we built was Redleaf. It's a clean slate operating system in Rust. So essentially, we're exploring language safety and its impact on operating system architecture and design. And we're building a couple of new ones right now. They're still private, but they are fun. If you ever want to see who I am, you can click here. This URL should open. You see my webpage. So essentially, yeah, so operating systems is kind of my passion. So that's why I'm really enjoying teaching this class. I taught it roughly for maybe 5 to 6 times. My first attempts were not very successful, obviously, but with the years, I guess I learned how to do it better, trying to deliver the best I can. Again, we are in a mixed graduate and undergraduate class. It's not really clear to me what the difference will be between the classes. So most likely graduate students will get harder assignments and maybe more engaging homeworks to a degree. But I think I've done it here once, a mixed version, but it was a class which is aimed at undergraduate level, but don't get me wrong. So this is very advanced in the graduate class. So if you're a graduate student, you never did OS, or you did OS, but it was some kind of not a real OS class. This is again the class for you. So we're roughly half undergraduates, half graduate students here in this class. So class webpage, and I will publish the syllabus on Canvas and on, okay, hold on. Oh, no. Firefox is up. Almost. So essentially, the Canvas will be our official medium for communication, meaning that all official announcements and deadlines will be on Canvas, but majority of the information will be on this web class, on the class web page. So everything from like, essentially, this is your kind of landing page, and the Canvas will have a link to this page as well. The idea here is that we will have Canvas for deadlines, so you can add them to calendar and track of what's going on. Grade scope for submitting homework assignments and quizzes. Everything will be electronic, besides maybe midterms and final, which might be on paper, but might be electronic as well. And if you decide to create a grade, what is it called? What's your favorite online to Discord, right? So if you decide to create a Discord channel, I will join as well. We'll try to be there, helping you, answering questions and stuff like that. So again, so here it's a rough schedule. So we are again exceptionally lucky this quarter because we're not losing days. So all the holidays are on Monday, and so we're Tuesday, Thursday. So we'll have a bunch of time. And towards the end of it, which actually never happened to me, which is again amazing, we'll have a bunch of additional topics which I always wanted to cover, but I never had time. But this quarter, I guess, we'll have time. Kind of security related and virtualization related topics, which are kind of advanced, right? So that's cool. So I'm happy about it. If you are curious about what was happening in the past, there is this link to the previous version of this class, which I taught at UC Irvine. And again, I'm pretty open about what's going on in the class. So everything is available online. All the previous homeworks are available, besides maybe quizzes, because quizzes, and I will talk over it in a second, but quizzes will be timed. So they are like just designed to help you to be on track every week. So they might be like hidden a little bit, but exams from previous years, homeworks are available, right? And the class repo is actually public. So if you feel like there is something which deserves to be fixed in the class repo, just make a pull request and I'll merge it. Same for the lectures. So I mean, sometimes I fail merging PowerPoint or whatever open office slides, but I tried. And so what I'm trying to say here, yeah, so you can scroll through the schedule. The only thing which happened, Zoom successfully deleted all my recorded lectures from the past. There will be some years which were recorded not through Zoom, so those are still available. I will try to recover something from past years, but again, it's not necessary. Just if you're curious, you can take a look at what was done in the past. Yeah, so you always, for every lecture, there will be like stack of slides, PDF. If you ever want to get to the source, you can open the web page, sorry, and just cut the end of the URL. You will get to all the materials which is related to the class. Sometimes there will be bits of source code and stuff like that, right? So, but again, everything is open and publicly available. So by and large, there is no idea of surprise you with anything. Just the idea is to teach you or engage you as much as possible and teach you as much as possible. So that should help. Something I wanted to say, homeworks. Yeah, homeworks. Okay, we'll get to them like in a second, but I wanted to say that some people like to start on homeworks early. You're fine doing that, but we do modify homeworks from year to year. And especially again, this year we have a good chance just because we have more time. We say the team, the TAs and myself are teaching us. And the idea is to first prevent cheating. At some point, our homeworks end up online and like all over the web. And at some point, preventing like straight copying is hard, but we'll do some modifications to make sure that it's not as straightforward. So that said, I mean, like, go ahead and start on homeworks, but don't to be honest, it's hard to start on homework without having prior experience with this class, but it's doable. So what will happen in this class? So the class was originally inspired by this MIT 6.828 operating system engineering. So it's a class which a couple of people started at MIT. The idea was to learn operating system by building them. And what MIT was doing is that there were kind of two parts. So one part was they learn a Unix-like operating system, and in parallel, they build a Unix-like but microkernel operating system, or if you like, library OS operating system as homework. So of course, that turned a bit too hard for undergraduate students, especially outside of MIT. So we kind of up the second part. So we will be doing just learning this operating system and working with the real source code of that operating system. But the homeworks will not ask you to build your own operating system. Although maybe graduate students will have to do something like that, we'll see. But undergraduates will not. And the assignments will be essentially modifying this operating system source code, right? So that will make it kind of like practical for us so we can actually finish. But the idea is, again, if you click on this website, this one actually lands you to the 2018 version of this class at MIT, but they updated versions which are like most recent as well. And why was it done this way? So the reason is when I first taught this class, I kind of decided that maybe that's the best way to teach. The advantage is that you will be working with this tiny Unix operating system, which you will have to kind of read the source code from top to bottom. It's only 10,000 lines of code, so it's readable. 10,000 lines of code. It's a lot, but over the course of a semester, it's totally doable, right? And then you know everything kind of, but it's real. It boots on real hardware. It creates processes. It's actually the history behind it. It's re-implementation of a Unix version 5, which was designed to run on PDP-11 machine, but in a modern x86 architecture. So that kind of makes it like very, very real and tangible. So this operating system is called xv6. It's, as I said, Unix version 6, but for x86. As I said, it's a relatively simple operating system, but nevertheless, it's a complete Unix thing. So it can actually, with a little bit of hacking, I can start running Apache web server on xv6. It's enjoyable, so that this tiny thing can actually run real software. And let's take a look at this xv6 thing. So here's an MIT web page, which says, okay, a little bit of a background. Again, public repos to download the source code. And this is actually the original book, which was describing the original Unix version 6 architecture. So I can make it larger so that slightly. Right. So the way what's good about the MIT's class is that they actually wrote their own version of a book, which describes this xv6 implementation. And this is actually the book which we will be using in this class. So written by the three people, Russ Fox, Franz Kashuk, and Robert Maurice, professors at MIT. It's not a giant book, so it's an openly available PDF, roughly 100-something pages, right? But describes enough of operating system details. And it actually, what's interesting here that at some point it gets to the details of actual implementation. Let me just scroll. I just wanted to find you a couple of examples where it refers to a source line. So something like this, for example, 1735. right? So this function walk page directory is part of this x86 operating system kernel. This line is where this function actually is printed. So the book itself comes with a printout, which is convenient, printout of the source code, and I click on it. And if I go to this source line number, hold on. No. Okay, mouse click doesn't work anymore. It's okay. 1735, right? So if I do Control F, here's 1735. First of all, it has an index which says, okay, really this walk page directory starts at this line. So if you really want to see where the function actually is implemented, you can look it up in the index. But this is essentially the implementation of this function, right? And I'm not saying that you should use this printout to navigate the source code. It's just one way. So, and it's fine. So you can use Microsoft Visual Studio, cross-referencing. Usually it's easier, but if you're in a hurry and it's an exam, you can open the printout and take a look at the implementation, right? But essentially, that's the goal. So you have to like read this kernel line by line, and I will be explaining what the functions are doing at a high level in the class, sometimes at low level as well. But the idea is that if you read it fully, then you understand it as well. It teaches you as well an interesting skill. So skill of reading the source code, because in real life, like all these complicated projects like Linux kernel, web server, just come up with your own example. Like the only real way to start modifying them is to read the source code and understand what they're doing, right? It's reasonably hard, but doable. So, okay, so this is one book which we're going to be using. Comes with a printout. Book is reasonably short. So we'll be using a lot of additional materials as well. So just a slight overview of assignments. So we'll have 5 to 6 homeworks, and there will be a couple of simpler ones, but all the homeworks are actually called something. So there will be nothing really on paper. So it will be coding and coding in C. So that's kind of a warning that you need to be able to code in C in this class. So examples kind of like, I will teach you how to work with make files, the basic compilation of Hello World program on Unix, just in case you never seen it again or never seen it before, just again to make sure that no one is surprised. Some homeworks which will teach you how to use GDB, again, the way to debug the kernel. There are multiple ways, but still GDB kind of is your number one tool. And if you understand GDB, then you can move to different other tools as well. And, something like ELF loading, essentially how you load a program in memory, start running it. And the bigger ones will be something like build a shell. I'm pretty sure you already build a shell in other classes. I mean, did you? How many people did build a shell? Not. So maybe less than a quarter. So, okay, we're not going to waste a lot of time. So you guys will have to build yet another shell. Unfortunately, extend this x86 with a system call, but usually with a tricky one, kind of something related to virtual memory. Maybe build POSIX threads, something about file system. Again, we have more time this semester, which is great. And in addition to this homework, there will be a quiz every week. It's a simple quiz. It will be timed, meaning that you will have like maybe 40 minutes, 30 minutes, 40, maybe an hour to take it on Gradescope. You can take it over the weekend, anytime. But when you start, you have to finish within like 30 minutes, for example. Each time I will give you the amount of time is given, it's proportional to the complexity. And this one is designed to make sure that you work through the week of material in the class, right? Because it moves fast. And it's like before we introduced those quizzes, people were like falling behind and were like, okay, what is going on? So you have to every week, by the end of the week, there will be a quiz, like probably this week as well. So which will force you to essentially watch the videos if you are not in class and be able to answer those questions. We'll have a midterm and a final. most likely the midterm is a week before the spring break, but let me just take a look at the schedule one more time. Again, I'm very flexible about grades. Don't think that grades should be given because they're kind of like to label you as a good or bad student. It just doesn't really mean anything in real life. I've seen students who get the worst possible grades still do very well in life or just very creative. So, but nevertheless, university asked me to give you grades, but everything will be curved. So I historically give hard exams just because if you're a photographer, you know this idea of a histogram, right? So exposure, and I want a curve which shows me, everything, not just, everyone is white here or everyone is black here. So that's why the median will be around 60 out of 100, but the curve will work if the max is 100 points and the max score which was achieved in class is 85. 85 becomes the max score. Right. Historically, there were no problems with grades. They are so badly curved or so well curved that you shouldn't worry about it too much. Other people do worry, so feel free to ask me questions later. Rough distribution of grades as homeworks are half, quizzes 15, midterm 15, final 20. Late homework policy is that you can submit any work besides quizzes 3 days after the deadline for 60% of your grade. Right. So if you miss the time, then you have 3 days to finish. Okay, let me stop here. By the way, feel free to interrupt me anytime. I should have offered sooner, but okay, any questions right now? Usually people care about grading and stuff. That's why I decided to stop. Yeah.
If you're a minute late on the day, it will just be at 60.
Yeah, I always say yes, but then when I receive this email saying that was a minute late, okay, what am I gonna do? You'll be fine, I guess. If you're a minute late, yeah. Although it creates pain because we have to do stuff with your homework. So yeah, I don't have strength to say no, I guess. Anything else?
So the homework's be done on the lab machines, or can you do them on a person?
Oh God, that's a good question. I forgot. At UCI we were doing them on the lab machines because they were used as a reference environment. So everything will be usually in the past. What we do is that we set up an auto grader on grade scope. So grade scope starts a container which we somewhat control, but that's your reference environment. In most cases, so this is no matter where you do the homework, it has to pass the test on Gradescope. We can get into the argument that, I did it on my machine and Gradescope implements something very, very differently or slightly differently. And sometimes your outcome is different. But typically people who get to this point because they upload multiple times on Gradescope, watch their grade until they get to 100%, right? So at that point, it already works, but it happens occasionally. So I should figure out the status of lab machines here at Utah, so you can you have at least an environment in which you can work. So historically, we were supporting lab machines, but people were using either their own Linux laptops or Windows subsystem for Linux on Windows. And occasionally you can work with Mac, but okay, Mac deviated in the hardware architecture these days, right? So it's ARM now again. M1 and M2, right? So it will be a little harder. So I would say lab is a good reference environment, and then it will work. Yeah.
So on Gradescope, would you know any of the results about the center or the accepted test?
You mean how we set up an auto grader?
Yeah, the auto.
It's just I think we fail to set it up on the day of assigning the homework, but maybe we usually do actually. And at some point it becomes available and you just submit and it gives you a score. And I hope there are ways to cheat, but hopefully you're not going to do it. We occasionally review and you say, okay, I failed it, but I built it. Then we can look into the source code and give you a grade.
So will the tests on break still be hidden or will it show the outputs?
We usually show the output. The question is whether the tests, whether we make tests available. Does it matter to you that much? We can make them available, I guess.
Yeah, because like there might be cases where like maybe there's extra space in the output, but if the output's not shown.
No, we usually like I think it's pretty lenient. So there is we'll figure it out to make sure that you're not gonna fail, like in some weird way.
I can't see these scores on panels.
Yeah, so I have to publish it. So just give me a sec, and I will publish. And I think it will be cross-listed to graduate and undergraduate. So let's check. I'll publish right after the class, and we'll check that communication worked by sending a message. By the way, did I mention Piazza? Right. So questions are on Piazza, and the Piazza is set up. So, sorry. I wanted just to make sure that. And the sign up code is on Piazza. Oh, okay, it's right here. Just quickly switch back. Right, so here, so yeah, I try to read Piazza in live mode, so not a daily digest, and I will try to be responsive. Usually, myself and TAs, I will try to ask TAs to help as well. But so sign up on Piazza to ask questions. But again, Discord is a good way to get an interactive discussion going as well. Any other questions about the grading homeworks? Again, usually in a class of 200 people, maybe a couple of people fail, a couple of these, everyone else is about to see something. Lots of A's and B's, and usually not a problem. So the second book, which we will be using, I said that we will be using a ton of additional materials, and they are listed on the web page. Sometimes it's just printouts or 7 blog posts, because sometimes people talk about the problem which I want to discuss in class. But we will use bits of this operating systems in 3 easy steps or 3 easy pieces book as well, written by another couple from University of Wisconsin Medicine. Andrea and Ramsey Arpasi, you saw. And it's also an open source book. You can donate them money, but it's available as a collection of chapters. So you just can, click at this on the link here. And if I assign something, I will provide you a link, and the PDF is available for you. So no need to buy it as well. And we're not going to read the whole book, but 7 chapters, especially in the beginning of the course and later on, because people don't know what process is. And okay, Ramsey and Andrea, they took their time, they wrote about it. The book is as good as anything else. I mean, it's a little wordy, but sometimes it is helpful. So we're going to be using that as well. Again, course organization, although I was already talking about it. So live lectures in class, I encourage you to come. I'm not going to check attendance, but if you really want to learn, you should ask me questions, because things will be moving fast. So if you are just watching lectures online, you're losing kind of half of your ability to learn. Why it's useful? The class is useful because, job interviews and just many different things are built on understanding how a grading system works, essentially optimization. If you like doing some cycle level optimization of your code, I don't know, working for a trading company or for whatever, work on scalability, work in the security area, you need to understand this. So that's why it's kind of useful. So again, reading of the book, x86 plus the source code, bits of this operating system in 3 easy pieces book, homeworks, which are parts of this extending x86 kernel, maybe some design riddles, and I will ask you how to build this feature. And sometimes it's a homework, sometimes maybe it will be on paper or electronic, but we'll see. So essentially, what are the prerequisites? So the course is kind of self-contained. The fact that you took an architecture class or computer organization class will help you to understand, but it's not necessary. So the way it's built, and it assumes that the only thing you know or can work with is the C programming language, right? So why C? Because this real kernel, I mean, you can write kernels in different languages, but surprisingly, the simplest kernel is still C. You can do it in Rust. We'll take a look at the implementation in Rust. You can do it in C++, even Java, but Java needs a runtime. Rust doesn't need a runtime, but is a funky language, which I like, but it's a little harder. So C is your easiest thing to do, unfortunately. Although, as this joke says, C is not as simple as it looks like. And for example, if we go back to the source code, let me just scroll here. So let's just go to main, for example. Quickly, just oh, that's a different main. There's a couple of mains here because, for example, this one, boot main, and it's part of the bootloader. And some people say, okay, what is this weird style? Just the 2 spaces as an indent. It's done specifically to be able to print all the source code in the PDF. Otherwise, if it's large, it just doesn't fit on the page. And they say they use a very short names. So for example, PH stands for program header, EPH, entry program header, I guess. So entry function. So it's a different style. So you might get used to the style, which is long names, and it's okay. It's just a different style. If you spend a little bit of time looking at this, you'll be just fine. You will find that the code is elegant. The people who wrote it are quite good, actually. So just don't immediately, create a negative feeling about it. It's just fine. But you will have to understand lines like this. So who knows what does it do? This line. Yeah.
Assigning a fixed address to that out point where it's going to run something.
All right, exactly. So elf is declared as a pointer, this funky star, to a data structure which is struct program header. And you say, well, normally you get it from malloc or in C++ class from a new operator, right? So, and this is the data structure on a heap, sometimes on a stack. But here they say, okay, we know where it is. It's in memory at address x10000. And there is a reason why it's there. I will explain the reason, but you have to understand that, okay, this is what's going on. The pointer in memory doesn't always come from the new operator in an unsafe language, right? So like C, you can do those tricks. So we'll try to help you with pointers, but that's essentially, normally, if you code C in a decent way, it's not much different from any other language, but the the essence of building those low-level systems is that you will have to manipulate with pointers. And this is just one example. So prepare for that. So it's not super hard, but a little bit confusing for people who never seen it before. Great. Any questions? But yeah, there will be fun. Okay, I got asked this question: how to succeed in this class? Read the source code. Here, my regular story, which I keep telling, which I actually got told by my TAs. There was a student at the University of Utah, when I once did this class at the University of Utah a long time ago, and my TA said, okay, on the exam was hard, final. Everyone was like searching through the web or something because it's an open book. Right now we do not allow internet search because the answers which we get is just like, they are ridiculous, right? They don't make any sense. But everything else is available. Books, materials, everything will be saved. And like, you don't have to save it on a hard drive. We'll let you open it online, but just no search. And everyone was searching, but this guy was, digging through the source code. And that's really the answer to succeed. So the question was about the source code and how it works. You cannot find that online. I mean, maybe someone else asked the same question online, that's possible. But really the question was designed to understand how operating system does something. And the answer was hidden in the source code. So you have to read it, right? It's unusual, but again, it's doable in this class. And read the book and stuff like that. So again, my advice, don't get scared. The class is reasonably hard, but it's not designed to be hard. It's just, I want to prepare people who can, work for me potentially after doing this class, or at least talk the same language with me, right? And it will help you in the long run with your job search and careers and stuff like that. But originally, it gets a little hard. Yeah, a little bit of homeworks are a little challenging, but again, we're generous graders usually. Again, we never seen a lot of problems with grades. So don't get scared. That's the point. And don't get, I feel bad about it. It's not easy to learn this, but if you do it, I think it will help you. Okay, so that's the end of my part one of the logistics, and we will get into the introduction in 2 seconds. Are there any questions about it? All good? No one is scared? Good. You shouldn't be. Just again, my advice: if your C skills are kind of rusty, then spend this couple of weeks reading this Kernighan Ricci or some other C book. And I think I link a couple from the webpage. Where's the webpage? And I even assign them, especially pointers and stuff like that. Maybe there will be something in some additional materials, this one. So C programming language by Kernighan and Ricci. So I think the first edition of this book is available on the archive, so you can read it, or any C book rather. So you can read the source code and program in C. Okay, let's take a short break. Usually we will not have a break, but today there will be a break. I'll try to boot something on my machine. So enjoy it, and we'll move on to the introduction. Okay, guys, let's continue. Let's try to understand what the operating system is. The break is a dangerous thing, so everyone wants to chat. You guys should go for coffee after. Okay, but anyway, so my goal here is to quickly. I don't think I will be able to finish in 30 minutes, but we will continue next time. But the goal is to quickly give you an overview of what operating system is, right? So because after all, that's what we're trying to understand in this class, right? So before doing this, let's quickly recap how computers work. Because I mean, if you just came out of my computer organization class, which is kind of an undergraduate level architecture class, which teaches you what's inside the computer, what's inside this thing, right? So you're fine, but everyone else might have a little bit like a rustic memory about it. So roughly speaking, so when you buy a machine, right, and some of you, I'm sure you were assembling your own desktops. I mean, it's maybe it's less common today, but back in the days, the way to go was to buy your own machine, like buy a motherboard, buy a CPU, assemble it together, very simple, kind of Lego, everything fits as long as it's compatible. And typically when you buy a CPU, which is here on this screen, right? I will be using pen here to highlight. It's a processor. It's made by Intel. There is a silicon die, and this die will typically have multiple cores, right? So a typical setup for a laptop today is 4 cores, and I just draw them here as 4 different pieces, right? So it's 4 cores. Modern machines implement a concept which is called hyperthreading, right? So it means that each core has a pipeline which executes instructions, and it pretends to the external world or to the operating system that it actually has 2 cores. In practice, it's just 1 core, 1 pipeline, but it's shared between 2 threads of execution, right? And that's why you have those 2 logical threads per core, right? 4 cores, 2 logical threads. If I ask my machine how many cores I have, the answer will be 8. So for example, if I switch to my shell here, I do something like, let's just clear everything, something like cat proc CPU info, it will show me all available CPUs. And if I grab for example, model name, I will end up with 8 lines, right? So it pretends to have 8 cores. In practice, it's just 4, right? It doesn't matter for the purpose of this class. It's just like bits of general knowledge here, right? Normally, the way the CPUs which we use today, they work in the following manner. There is always a memory attached to the CPU. CPU is kind of stateless, at least when it boots, right? And it has a little bit of memory on chip, which is typically called registers, and there are caches and stuff like that, but caches are just for performance. Functionally, you only need registers, right? And all the programs and everything else is stored in that memory, which is a different chip. Typically, again, you buy it separately, you plug them on the motherboard, right? And this is the picture of this tiny chip. It's called DIMM, Direct Inline Memory Module. Essentially, it's a random access memory. Again, you need to take an architecture class to know how it works, but it doesn't matter. What you really need to know is just that it supports 2 operations, reads and writes. If you write a value at a certain address, the write operation returns nothing. And the memory is byte addressable. So you can say, I want to write a byte of information, right, into this address, and it will store it. Store means that if you read the same address, you will get the same value back, right? The most recently written value. So that's not super hard, right? And if I ask you the question, so, okay, sure, we got this. There is a CPU, there is memory, but what is a program? So CPU internally is also relatively at a high level, exposes a relatively simple interface. Internally, it's super complicated, lots of optimizations, security vulnerabilities, whatnot, right? But at a high level, CPU executes this loop over and over and over again. And silicon, again, if you took the architecture class, you know how to build this pipeline, at least the simple version of it. And typically, there are 2 special registers on the CPU, right? What are the registers? It's just like 32-bit or 64-bit values, right? Or it's a tiny memory. It's very, very fast. CPU can access it within the same cycle, but it holds some values which are important, right? And so two registers are special. One is called instruction pointer in x86 architecture. In MIPS architecture, it can be called program counter, right? So it's the same. So it's a register which contains the memory address. So here I have memory. This is my memory instruction pointer, and this R stands for 64-bit version of this pointer versus IP will be 32-bit version. So just the naming. It just contains an address. And in memory, there will be some kind of an instruction. Maybe it's an addition. Maybe it's a made up for instruction right now in this example. So what I say it does, it just takes 2 values in 2 other registers. One is RIX and one is RBX. Again, R stands for 64-bit versions of those registers. AX and BX historically had some meaning. AX was for accumulator register. Now it just doesn't matter. So this architecture names them. x86 architecture names them in a human readable names, which don't really mean anything besides stack pointer and stuff, but other architectures just will name them register 1, register 2, and such. So it doesn't really matter. And push the result back into the third register. So by the way, we will go through the x86 assembly, maybe not this week, but the next week. So don't get scared. So I will teach you how it works, and not super hard. But essentially, instruction read sits here. So, and you can guess that your program actually sits somewhere in memory, right? And what CPU does is the following. So it says, okay, I will first take a look at what my current value of the instruction pointer, right? Because maybe it has changed. Maybe there was an exception. Maybe there was a jump, stuff like that, right? Let me take a question.
When you draw memory in this class, where should we assume 0 is at the top of the bar?
In this drawing, it's 0 is at the top, and this is the max. And we might alternate. Just when it matters, I will show the other system. When it doesn't matter, it just doesn't matter. And so, but it nevertheless, so CPU logic internal, this is built in silicon, which means that someone programmed the logical gates for you, the designers of the CPU, using some high-level programming languages like Verilog, and high is not probably as high as you want, but essentially that's at the level of logic gates, right? Everything which is on the left. So normally naturally what you do is they say, okay, the first thing we'll fetch this instruction from memory, because you need to understand even what this instruction is doing. So you just essentially, CPU just reads it from memory, right? Because CPU is stateless, right? By and large, besides the registers. Then it decodes the instruction and says, okay, is it an addition? Is it a subtraction? Maybe it's a for instruction invoking a function. So there is a logic on the CPU which decodes this instruction and realizes, okay, this is an addition. After that, it's kind of, you say, okay, addition has a couple of operands, meaning that, let me just clear everything here. It has 2 input operands, so kind of RAX has to be added with RBX, and the result will be placed in RDX. Let's assume, for the sake of example, so it might not be true, like not a real instruction. But so CPU says, okay, what are the values of RAX and RDX, or RAX and RBX? Okay, there are such and such, maybe 5 and 10. And then there is a logic which executes addition on the CPU, right? And 5 gets added to 10, result 15 gets placed into the register RDX, right? And there might be a fault. Maybe you're trying to access a memory which is not mapped. And this is when you get a sec fault. And we will get into the details how the sec fault is implemented later. Or maybe it's a division by 0 because, it doesn't make sense to move forward since you're dividing by 0, the result of your computation is not defined. So at this point, the CPU raises an exception, and hopefully, the operating system or the runtime will take care of it. Maybe the page fault will map the page back, stuff like that. But if the fault doesn't occur, we go to the no pass. We commit those results. We say, okay, this result, which is 15, now has to be permanently stored in this register, right? And it's okay. So you say, what's the next step? You say, well, let's take a look at what has to happen to this instruction pointer register. Because normally when you say it's an addition, so you want to go to the next instruction here, right? Because it's logical. Your program is here in memory. We will learn how this program gets loaded in memory from disk, stuff like that, right? So don't worry about it right now. But normally it's just the address of the next instruction. And sometimes it's a jump. If the else statement gets compiled to a jump, the value of the instruction pointer gets changed, right? And you repeat it again. So it's fetch, decode, execute loop. So this is the CPU at a high level, right? Kind of easy. So any questions? Again, the goal is to convince that everything is relatively easy at a high level, and then we go into the details. So CPU executes instructions one by one, right? Not a big surprise. Modular jumps, and we will take a look what happens to those and stuff like that. So if I ask you a question, so what is an operating system then? Any guesses?
Kind of just functions with the task manager.
Right. So what you're saying functions as a task manager. So what do you mean by that? I mean, first of all, there is no single definition. If you go into this operating system domain, people will start fighting about what really belongs or doesn't belong to the operating system. But broadly, and it doesn't really matter that much. In many specific cases, it's like it can be different. But what you're saying is that it's a task manager. But what you really mean by that is something probably like that. So you say, first of all, I care about my, I don't know, maybe I have a digital sensor like embedded somewhere in this room, and I want to read the value of my sensor, the temperature. I just want to run this main program on a piece of hardware which I bought. You know, some maybe you went to a store, you got some funky CPU, maybe not x86, but something simple like MIPS. You say, I just want to run it. So you say, I want to program in my favorite language like C, where you have your main function. And really, at this point, the goal of the operating system is just to help you to get to this main, right? You don't really want anything else. You say, I have my tiny program, it reads a sensor, just get me to main. So essentially, you just want to boot essentially on this piece of hardware, because like, who knows this CPU, what does it even do before main, right? And so at some point, operating system, and I will be drawing it in this, I will be drawing yellow for the operating system and green for the user level part. This is the program which you want to execute, right? So this tiny yellow piece is your operating system. And like, again, if you're building a startup and you say, look, I want to build a wristwatch or something, maybe it just shows you the heartbeat. That's an example. You say, I don't really care. No switching of tasks, nothing, just get me to main and maybe put something on the screen, right? So how you do that? You say, well, I really need to build like a tiny piece of code here in this yellow part, which understands where the CPU, what happens when the CPU turns on, when the power is on, right? And then somehow gets me to main. And after that, I will be fine. I will be executing here. I'll be super happy, right? That's your operating system, like the simplest you can get to. Kind of people call them embedded operating system because they are as simple as this when you look at embedded devices, and you really can't do much more just because you have only so much power, and sometimes you even harvest energy from the environment, right? So you like from solar panels or vibration, right? And you can't really allow anything else, right? And essentially, this is kind of the beginning of this, how the operating system starts. Nothing, just get me to main. Well, you say, remember my example with the wristwatch, you say, well, I wanna print something on a screen really naturally because you want some output, an input, obviously. And you say, I want to build this printf function, which, takes some human readable string here, maybe and some values like A and B, and will print something on the screen. And you say, well, how do I do this? You read the manual really, which often boils down to move instruction is just allows you to write memory on x86, right? And so you say, often to show something on the screen, and you have a hardware screen, which hardware people build for you, you just write values into some magical locations in memory. And then the screen hardware picks them up and just visualizes them for you. So you say, look, I will build this because it's okay, and it will show up on a screen, but you say, well, really, my device hierarchy might be a little bit more complicated than just one screen. And this is a realistic architecture of a modern machine. You have a CPU here, you have this memory, which I was showing, it's connected through a memory bus. You can think of it as a tiny distributed network, more like a Ethernet network, actually, rather than just a collection of wires. You have more buses. There's this PCI bus, which connects majority of devices today. And so somewhere here, you might have a network interface, Ethernet or Wi-Fi. Somewhere here, you might have connected a solid state disk, NVMe disk, or PCIe attached SSD solid state drive. Below, there might be even more buses. SATA bus allows you to connect hard drives here. USB bus will be connected over here. So it gets a little bit funky, and you say, like, I don't really want anyone who wants to write a printf or write something to disk to go through those low-level details of how do I even get from like which memory location I have to write to land somewhere over here, right? That's a little hard. And so you say, look, I will, instead of like putting this code in a program, like this code, just essentially what it does is says, if I have a VGA screen, kind of a real screen attached to my machine, I will do one thing. And if I don't, then I will put the output on a serial line. Serial line is just like a cable which allows you to read these values from a data center, for example. And what I'm saying here is that instead of doing this, the operating system developers will provide you a function. They will provide something what is called a device driver. And in this example, it's a console device driver. And will provide a high-level function for you to invoke, which is called putchar, for example, in this example. And you as a user can use it. And this whole complexity of moving something, everything what I was trying to write here gets moved in the operating system, and operating system kind of says, okay, becomes a library which provides some useful functionality and hides some obscure details of what the hardware is doing, right? Which helps you to actually run this program on even different piece of hardware, because you say, look, today I'm running on MIPS, tomorrow I might recompile, but the same code will run on x86, just because the operating system will provide the same interface, right? Agree? So you say, okay, my operating system now is kind of a funky library which provides me access to devices, right? Hardware interfaces. So, okay, that's step number 2, but again, not super scary yet. So essentially, it's a piece of code, this yellow piece of code, which abstracts the hardware, provides high-level interfaces like putchar, hides differences between hardware implementation. As long as it's a screen, it will help you to output letters on the screen, but you don't have to think about the details. It can implement some optimizations like request batching. You submit network requests in a batch. Instead of submitting one packet at a time, you will submit 32 packets, but you don't really care. And that's essentially what operating systems are doing for virtually any piece of hardware, graphic cards, disks, network interfaces, consoles. We'll talk about how device drivers are implemented later on in class, just a high-level overview. So at this point, your operating system is more like a library, which provides these useful functions. But then you say, okay, again, my wonderful watch, but it has an alarm, which wakes me up. And normally it shows me time on the screen, but alarm has to start running, at a certain point in time, when for the time for which I set the alarm, and which means that really those two things have to kind of run in parallel, right? So you say, maybe this is my watch for time, and this is my alarm. And you say, look, I have one CPU. So what do you think needs to happen? So you have two programs which you want to run, but how do you do this? What's the trick?
The CPU sets the timer and he says, well, I'm going to stop you now with an exception and then switch to a desk.
Well, that's a good answer, but what you're saying is that you're assuming that the hardware has a notion of a timer, and it can essentially, you can say, look, I ask you to interrupt me in, let's say, 20 minutes, and then it will raise an exception, right? That's not always the case. So that's not how timers are often built in real life, although this also can be achieved sometimes. But what I was trying to ask is, how do you really share hardware between multiple instances? Like you have two mains. You compile them, one is green, one is blue, and now what?
Would they be on two different threads, for example, you have to schedule them?
Correct. Correct. In a way, correct. So what you say is that two different threads, but the question is, what is a thread or what is a process? Remember, I was drawing one memory here on the side. And what happens in real life is the following. So this main will be sitting somewhere in memory here. And at some point, operating system, this one, yellow part, will configure the program counter or this RIP register to start executing instructions from this first main function. The operating system will have enough logic to load this second main somewhere else in memory. right? So it will be ready to run, and it will be using either this yield function, which says, okay, I'm done running. And then this point, if you do a yield, you may be exit into the operating system, which also sits somewhere in memory. The operating system says, okay, I see that you don't have anything else to do, so I will switch and start running this second main function, the blue one. So let's say this one is a green and this one is a blue. So which means that it will configure the CPU instruction pointer of a CPU to point to this location in memory, right? And CPU will start doing this fetch, decode, execute loop from here, right? And essentially, maybe this program at some point says, okay, I'm done running as well, and it's called cooperative multi-threading. And again, it will exit to the operating system, and the operating system will decide, okay, it's time to run the green program again, and we'll just switch back here, and we'll continue running the first green main from here, right? So what happens is that this yellow piece somehow can tell the CPU where to start running, and it will be switching between those locations. And for you, as a user, the switch will be so fast that you can't even notice, right? Because on my machine right now, we run whatever, PowerPoint or OpenOffice, Zoom, and 200 other processes, right? And the CPU is constantly switching, and it does use a timer to say, okay, typically timer is used like in the following manner. It says, okay, is it time to interrupt the previous program? And if the answer is yes, the switch happens. If the answer is no, you continue running, right? So, but the point is that you will be switching between them instantly, like very fast, so the human cannot notice. There was a question.
Does the program author put the yields in, or does the operating system inject them when it loads the program?
Right. So in fact, today, this yield is not used anymore. So this yield was, again, the artifact of the past, where the operating system was not able to preemptively switch programs. Preemptively means using a timer and occasionally saying, the timer essentially is a hardware thing, like your classmate was mentioning, which essentially periodically sends something what is called an interrupt to the operating system. And the operating system takes control and makes a decision. But for a while, the scheduling was actually cooperative. Early versions of Windows, like Windows 3 or something, were actually cooperative. If you don't have this yield as a programmer, you monopolize the system and you never exit. I think even early versions of macOS were cooperative, but that I'm not sure. But then later on, people realized, okay, it's a wrong model, because if you made a mistake and you forgot to put the yield here, then the whole system is screwed. And at that point, they designed a new model, and this is what we'll be doing in this class, where the timer essentially occasionally sends an interrupt, typically once per 10 milliseconds or once per 100 milliseconds. It's still so fast that you can't notice as a human, and sometimes you have those yields because you say, well, I'm about to read something from a file. It takes 10 million instructions. Waiting for 10 million instructions just impractical. So you say, well, at this point, let's switch to something else. So that's the answer. But essentially, what operating system is doing here is that it implements this functionality of virtualizing the hardware across multiple programs. And it virtualizes both CPU and the memory, because somehow, the memory is also shared between multiple programs. And I will explain how it's done. But that's the idea. And it's a very powerful idea, because if you ever programmed Arduino, like as a child, you quickly notice that, okay, it gets insane when you want to run multiple timers, and then, you have to program them carefully, because there is no multi-threading there, right? So there is no this functionality. So Arduino is more like a library, which never really switches you from one process to another. But modern operating systems do switch. And in a way, it's kind of like a car rental sharing, right? So essentially, you say, I have one piece of physical hardware, which is a car or a CPU or a memory, and just people or programs take turns, right? Essentially, the operating system essentially says, okay, I will enforce some kind of a fairness policy. If you pay enough, you will use the car long enough. If not, I will chase you and find you and take a car to someone else, right? So this time sharing is essentially executes concept because it allows you to run multiple programs on the same hardware. Again, my point here is that often it looks like magic. So what does it mean to switch from one to another? But my idea was to explain you that CPU is reasonably simple. It just does this fetch, decode, execute loop. And the place in memory where the instruction pointer is pointing is actually running right now. CPU just doesn't know anything about those multiple programs. It just executes instructions. But at the same time, the operating system, which occasionally takes control, is smart enough to pretend that, okay, you will switch between the programs and they will be run kind of in parallel, but really taking turns on the hardware. Okay, so let me stop here and then we'll continue from finishing this introduction and then going into operating system interfaces next time. Thank you. What's happening? Just stop Zoom.